I mentioned at the end of the previous video that I was having issues measuring current. Here's an extract of some of the data in more detail, and the blue is voltage, the red-orange colour is the current, and the grey is the turbine RPM. And clearly there is an issue here, and if we look at this graph of the current against the turbine RPM, we would expect to see a nice curve up here, and instead we get this. Now the reason we've got this here where it doesn't drop down to zero is that I put a small capacitor on the output of the amplifier. Not the best idea, and it doesn't work anyway. So I then went on to completely ignore what I said in this clip. I've checked the multimeter and the amplifier is giving a nice smooth output. Perhaps not the best word to describe it, but what I meant was that it was following the turbine's RPM and no evidence of it dropping out. So it's just a coding issue. And continued to replace all the wiring and the rectifier in the turbine and the dynamo itself. But of course this had no effect. Here's a closer look at the output of the amplifier. First at a sampling rate of 20 milliseconds, and you can see how it's interacting with the frequency of the generator's output, the current pulses. And if we increase it, this is 10 milliseconds, and you can clearly see the problem here is that the current comes as pulses from 0 to their peak value, and again at 5 milliseconds it becomes very obvious. You can almost see the individual current spikes. Very fixable with a bit of code writing, but I chose to physically smooth the output of the turbine as I had some large capacitors. And let's see what happens when we connect up the capacitors. And there we go. We've still got a little bit of ripple, but it's a lot better than it was before. And that's when it's disconnected. You can clearly see the current spikes going from 0 to the full value. I made a few little changes to the layout and wiring, and moved the connector block from this side over to there, so I only have wires on two sides now, which makes it a little bit easier when it's in a small box. So the current shunt runs around the edge of the board there. The current shunt's under the tape, and it runs around the edge there, which is okay because I'm only measuring up to 800 milliamps, so it's fairly low current. I've also got an extra 5-volt connector there, so I don't have to shove two wires into one connector for the two reed switches. And because I've moved that connector block from there, I've actually had space to add a Bluetooth module. Now that makes it a lot easier just to check that it's logging properly, rather than trying to get a USB cable into here whilst it's in a little box. So also it's not really a good idea when you've got the V-in powered to also connect up the USB. They seem to be okay, but I don't like doing it much. And the other thing to be wary of is that if you're powering this off the USB, it's a different voltage from its internal regulator, and so your voltage readings won't be accurate. And what I've just done is calibrate both the voltage and current, and that has to be done for the individual Arduino because they all have slightly different voltages that they're using as a reference. So I can go into that on the computer now and just quickly show you a very simple calibration process. You just go through different voltages on the pin that you want to record with, and you just on the serial monitor you just read off the value here. In my case I was transmitting via Bluetooth, ensuring that it was powered, the Arduino, by a power supply into its V-in, because that's what I'm going to be using when it's data logging. And again with the current, you just put current through the shunt and read the pin value, and these are the two graphs, and you just use this trend line, get the equation, and that's the value that you then put in to the Arduino's IDE here, for example, to change the reading to to a sensible value which actually means something. Well, finally I have a fully functional data logger. It seemed to take a lot more effort than I expected. We have the massive capacitors there for the current sensing to smooth out that. It's now all calibrated, the voltage and current is calibrated, and we've got the Bluetooth module transmitting to this phone. We've also got the code sorted, so the wind speed, the top graph, and the turbine RPM, the middle one, are now able to read right down to very low wind speed, and the RPM goes down to about 15 without any silly spikes where it goes up to its maximum. And at the bottom there is the current. We've also got voltage, and you can see that on the data here. So we've also got the averaging going, so it's writing to the SD card every 10 seconds and outputting data on the serial monitor every second. And I'm just going to leave it running for a bit and see what data we can get. Finally, let's have a look at some of the data that I recorded. This is actually at 1 second intervals, it's not actually averaged, and unfortunately the voltage readings seem to become disconnected. But we have wind speed in blue, the orange red colour is the turbine RPM, and current is the yellow one. And we were able to get this nice graph which I've already shown, and a power curve, which I had to make the assumption that the voltage of the battery was around about 12.6 volts, but we have been able to create an approximate power curve, and as you can see, it's not the most efficient turbine. You're only getting about 4 watts at around 30 miles per hour wind speed. And you can also create this graph here, which is the wind speed against the turbine RPM, and from that you can calculate the tip speed ratio. You can also get the efficiency from power and wind speed as well. This is now averaged over 10 seconds and recording for a much longer period of time. See, I think it was a 24-hour period. The wind eventually died, so I took the SD card and have a look at the data. Here we got the power curve, but of course because it's averaged you don't get the same high peaks because they're averaged out, so we only got up to around 12 meters per second. And this is quite an interesting one when it comes to analysing how much load the generator is putting onto the blades. So you can see that there's a cut-in RPM is around about 120. So up until there, the RPM increases, and then the gradient changes. This area here is where the generator is putting a bit of load onto the blades, and then here above this, then the RPM starts to increase again because the output of the generator drops off a lot. And we've got some more data here. Again, over, I think it was a 2-day period. So you can see I've also got a solar panel attached to the leisure battery, so that's when the sun came out, and the dips are when I plugged a phone in there. So that's a quick look at some of the data, and I would like to, in the future, use this to optimize the performance of the turbine. But for the moment the turbine is packed away as I've moved back to Wales, so that can be a future project. And that's it for this video. Thank you for watching.